Hi everyone, myself Dona Baji, research scholar, Center for Nanosciences and Molecular Medicine, Amrita Vidyapeetham. First of all, I thank International Conference on Energy Materials and Devices 2022 for giving me an opportunity to present my work on rechargeable alkali metal ion batteries with chemically reduced FeFeCN6 cathode. Energy is the lifeblood of modern civilization, and hence demand for the energy is increasing day by day. Figure 1 shows the BP statistical review of 2019, which draws out different primary energy sources being utilized, whereas the 85% rely upon fossil fuels. These fossil fuel energy economy creates serious issues and major climatic alterations like emission of carbon dioxide. This increased challenges prompt the researchers to focus on energy sources which are consistent, suitable, and safe, which has led to the interest to renewable energy like wind, geothermal, or solar. However, these systems are intermittent and prone to unpredictable variation. Thus, to avail continuous energy supply, it is inevitable to have efficient energy storage systems. Among various energy storage systems available, rechargeable lithium-ion batteries are attracted due to higher energy density and long cycle life and have powered billions of portable electronic devices since the successful commercialization in 1990s and are now utilized in electric vehicles. However, from this graph depicted, which shows the lithium distribution is mainly situated only to the certain countries, and as well as the lithium from used batteries is or recycling rate of lithium from the used batteries is only around 1%. Therefore, alternative low-cost storage systems having wide reserves are desirable, which can be used as large energy storage system. So the major focus turned to sodium-ion batteries, where sodium is the fourth most abundant in the earth crust and low cost, since a cathode and electrolyte composed of sodium-based compounds, which is economical, as well as aluminum, can be used as current collector for both anode as well. So the basic working principle of sodium-ion battery is illustrated here. The structures, components, and charge storage mechanism are similar to the lithium-ion battery, except the charge carriers are changed from lithium to sodium ions. The major challenge of sodium-ion batteries is this low energy density compared to lithium-ion battery, and a larger sodium ion size of 1.02 angstrom compared to lithium ion, which is 0.76 angstrom, which limits the diffusion of sodium ions to insert into or extract from host material, thereby influencing the overall kinetics and electrode integrity. So the cathode materials are the key components that determine the overall performance and entire cost of sodium-ion battery. However, the unstable structure and limited electrochemical performance make them difficult to meet the requirement for practical application. So today's various cathodes have been explored, namely just known as layered metal oxides, polyanionic compounds, and Prussian blue analogues and organic cathodes. Here, Prussian blue analogues is our material of interest due to FeFeCN6 ferrocyanide is a potential candidate due to its robust structure, which could tolerate numerous substitution and modification in the interstitial site without major structural change. So PBAs can be generally written as given as the formula AXMFCN6, where A is alkali metal and M is N-coordinated transition metal ion, and M dash is a coordinated transition metal ion. So our in this work, we majorly focus on NaX FeFeCN6, which is nothing but sodiated Prussian blue analog, and LiX FeFeCN6, which is nothing but lithium-containing Prussian blue analog. The sizable framework of these Prussian blue analogs allow cations to diffuse through the interstitial sites. Ease of synthesis, development, and tunability of structural development, as well as higher theoretical capacity due to the redox centers are added advantage of Prussian blue analogs. However, the major drawbacks can be attributed to the coordinated water, which leads to the lower utilization of theoretical capacity. So substantial efforts has been taken in order to develop Prussian blue analog without these issues by metal substitution, dehydration, surface coating, etc. So our experimental part mainly deals with a preparation of FeFeCN6, which has been obtained by a nickel ion source of K3FeCN6, and subsequently this FeFeCN6 was taken for chemical reduction to form sodiated Prussian blue analog, which is nothing but NaXFeFeCN6, which is named as CSFeFeCN6, where CS indicated chemically sodiated, uh, which is obtained by using NaI, sodium iodide, as a reducing agent in a solvent medium at 80 degrees Celsius for a period of less than 10 minutes at an ambient atmospheric condition. And similarly, lithiated Prussian blue analog were also obtained by adding lithium iodide in the place of sodium iodide to obtain LiXFeFeCN6. So the structural characteristics of all the samples were determined by a powder XRD. First figure, you can see that stacked image of all the samples, bare sodiated Prussian blue analog, lithiated Prussian blue analog, which is indicated in the lessons. So the bare sample shows a well-oriented and sharp crystalline peaks, and the samples belongs to typical cubic structure of FCC space group. And the sodiated Prussian blue analog also has similar crystallinity of cubic structure, whereas the 400 peak becomes stronger relative to 200 peak intensity, increased local electron density upon sodiation. So this lithiated Prussian blue analog also have similar crystallinity of bare sample, similar to sodiated Prussian blue analog. It is observed that 400 peak of lithiated Prussian blue analog also slightly increased upon lithiation. From the figure B, you can see that upon sodiation, 200 peak showed a peak shift towards the lower angle, indicating the lattice expansion, while the same 200 peak upon lithiation shifted toward a higher angle, indicating lattice compression. So from the figure 2, which displays the low magnification and high magnification field emission scanning electron microscopic images, and the particle size of the samples were uniform, and it was about 500 to 600 nanometer. From the micrograph, it is evident that the morphology of the samples are well-ordered cuboids in nature. It is revealed that the chemical sodiation didn't invoke any significant change in the particle morphology, while a notable size decrease of cuboids is observed for the lithiated sample, and it may be noted that lattice contraction was also observed in structural analysis. So the electrochemical properties of plot shows the rate study in figure B, and the corresponding charge discharge profile is indicated in A. The initial charge capacity of the sample was only 61 mAh hour per gram, whereas the discharge capacity reached 138 mAh hour per gram. And this indicates an incomplete chemical lithiation process. So the discharge capacity of lithiated Prussian blue analog electrode has been noted to be 138, 134, 125, and 100 mAh per gram at a specific current of 50, 100, 250, and 500. When the cell was again cycled back to 50 specific current, it recovered a capacity of 133 mAh per gram. So apart from that, the cycling performance was also conducted, and which is depicted in C. The initial capacity of the electrode was 118 milliampere hour per gram, and this cell has maintained a 92% retention in the end of 300 cycles, which is calculated from the third cycle. So it would require very high concentration of lithium iodide for increasing the lithium content for chemical lithiation, as the reduction voltage dips below 3 volt. Hence, the chemical lithiation using lithium iodide is not suitable reduction process, and an alternative lithium process is required. Nevertheless, this partially lithiated Prussian blue analog exhibit good electrochemical performance that the specific capacity in subsequent cycles and capacitive retention for the long cycling performance is very impressive. And from the second figure, which shows the sodiated PBA rate study, and the cycling performance was also studied, and the charge discharge profile was depicted in A, which shows a good initial charge capacity of 110 milliampere hour per gram at 25 milliamp per gram, where in case of lithium it was only 61 mAh per gram. So further from the rate test, it is concluded that the sodiated PBA is a good cathode for sodium-ion battery application. The rate performance has been conducted from 25 to 250 specific currents, and the discharge capacity it was delivered was 127 for 25 specific current, and at 250 specific current the capacity was 70 mAh per gram. When the electrode was cycled back again to 25 milliampere gram, it still could maintain a capacity of 110 milliampere hour per gram. So at a higher current density of 250 milliampere gram, the capacity decreased. However, as a future perspective, the capacity can be improved by a conducting additive. In order to further advance the knowledge towards the cycling capacity and the retention, the sodiated PBA cycling performance has been conducted and given in the figure C. So you can see that the initial 2 cycles were done at 50 specific current, and further from there we have done at 100 specific current. A 500 cycle data is shown, and a capacity of 78 milliampere hour per gram was obtained in the end of 500 cycle with a 70% of retention. And it has been observed that the trend in decreasing capacity for initial cycles, however, at the later stages, cycling stability improved significantly. So an approach to thoroughly understand in depth about the electrochemical properties of sodiated Prussian blue analogues has been implemented through ex situ analysis. So the first charge and first cycle in the figure depicts sodiated Prussian blue analogues first charge XRD and sodiated Prussian blue analogues first cycle. So first cycle means one charge and discharge. So the ex situ XRD analysis give more insight into the structural changes caused by the electrochemical activity. It may be noted that sodiated and bare electrode has similar XRD profile of well crystallized cubic structure, which is similar to the powdered XRD presented. So correspondingly, at the end of first charge of sodiated PBA belongs to well-oriented cubic structure similar to the electrodes before cycling. The closer view of ex situ XRD is depicted in B and C, confirms the phase transition. You can see that the high indents 200 peak shift to the lower angle upon chemical sodiation of FeFeCN6, which is indication of lattice expansion, followed by high angle shift during the first charge, which is due to the lattice compression upon desodation. So the lattice expansion again happens when the sodium is inserted back at the end of first cycle along with the phase transition. Similar observation was found in 220 plane also. So we observed a cubic chemically sodiated NaX FeFeCN6 with X is equal to 1.22 based on the first electrochemical desodiation capacity we have calculated. We have observed cubic to monoclinic phase transition at the end of first cycle when high sodiation NaX FeFeCN6 with Na is approximately 1.4 through electrochemical discharge was attained. So based on this result, it may be described that the structural phase transition from cubic to monoclinic possibly happens with a critical sodium concentration around 1.3 in NaX FeFeCN6. The transition is confirmed by peak splitting of 220 and 420. This monoclinic phase was retained even at the end of fifth cycle. The surface chemical analysis of the cycled electrodes through ex situ XPS study has been conducted on both the composite electrodes, both as prepared as well as cycling ones. Apparently, the sodiated PBA and first cycle shows similar Fe2P spectrum with Fe2 plus state, which is due to sodiation induced reduction, which is quite similar for both the electrodes with only a trace amount of Fe3 plus. So, as conclusion, chemically sodiated PBA and chemically sodiated chemically lithiated PP has been obtained from single ion source originated, followed by a facile low temperature come rapid sodiation and lithiation process. So the proposed chemically sodiated FeFeCN6 showed a better chemical sodiation, sodium rich compound formation, which has been concluded from capacity quantification during first charge. The obtained CSFeFeCN6 performed well as sodium ion battery, delivering a capacity of 78 mAh per gram upon completion of 500 cycles, about delivering a 70% retention. Nevertheless, the chemical lithiation process was inefficient, leading to lithium poor FeFeCN6 compound. So, however, the performance of lithiated PBA was better and manifested to deliver a retention of 92% in the end of the 300 cycle at a higher current density of 100 milliampere gram. So as broader perspective of the prepared electrodes has been explored by X-ray XRD and XPS study. The structural analysis confirmed by cubic to monoclinic phase transition at the end of first cycle, which may be one of the reasons for unstable cycling during the initial stages, which provides future scope for this work in improving the stability. Such a facile, cost-effective, rapid, scalable sodiation and lithiation process has been communicated for the first time for the best of our understanding. So this provides sufficient insight for preparing sodium-containing potential cathode materials. So in spite of all disadvantages of Prussian blue analogs process, most efforts are focused on sodium-rich Prussian blue analogs. So however, there are reports on PBS with incompletely sodiation. This demands a sodiated anode for practical application, which again leads to several hurdles from the commercialization perspective. On the other hand, our approach was to employ an atmospheric condition convenient way of synthesis method which avoid other high challenges like high pressure or reducing atmosphere to inhibit oxidation, etc. Our work emphasizes the importance of sodium-rich intercalating cathode material, which will further avoid multi-step processing or complicated electrode design. This has been realized to be a high-yield, high-efficient process which can be considered to be a practical approach. Further, this work will be demonstrated that chemical reduction could be a potential process for preparing alkali ion containing cathode material. So these are my references.